I'll try to pitch this because I believe it can be pitched at people who have basic quantum mechanics background but nothing else. So ideally this should be understandable starting from the point of view of knowing the quantum simple harmonic oscillator. So if you're familiar with that model, we'll be talking about a supersymmetric version of that model, which is, not that much different, except insofar as it needs to be. Okay, and today is going to be more kind of slide lecture-y, and then the stuff I have tomorrow will be more kind of classroom-y, but there should be plenty of time for discussion at the end. The last time I gave this talk, I had Shelley Goldstein interrupting me every 5 seconds. This time I should get through it a little faster. Okay, so as far as the very basics of what we're going to be talking about, right? You probably heard all kinds of talk about supersymmetry, some of it from people who are either these days kind of ragging on it, hating on it, or lamenting how badly things have gone for it. It's a bit exaggerated, but whatever. But what it is a conjecture, right? So it doesn't have any kind of direct experimental evidence of any sort in favor of it at this point. So keep that in mind in the course of discussing it. That there's no any kind of direct empirical evidence that it's true. But it's a conjectured symmetry of string theory and quantum field theories that go beyond the standard model, right? The thought is that there is a transformation that these theories are invariant under, which, this is kind of like the pop science version, which is essentially correct. You take a boson state and you apply a supersymmetry transformation to it and turn it into a state of fermion, of a fermion, right? Now, why would we look at it as philosophers now? I mean, essentially the answer is because it hasn't been done previously, and it is of great intrinsic interest. So it's absolutely true that they were hoping to find it at the LHC. How bad is that then? The flickering, is it okay? All right, okay.
Cool.
All right. So it's absolutely true that they were trying to discover it at the LHC and did not. But, of course, it's also true physics-wise that there's no restriction on which energy scale Susie can show up at. So I was the outside member of a dissertation committee for a guy working on his dissertation in theoretical physics at Michigan, and he was working on supersymmetry, and I was like, well, hey, how does your confidence, I tried to ask him this question from a Bayesian point of view. I was like, how does your confidence in the truth of supersymmetry, how would it change if we didn't find it at the next accelerator? And his answer was, well, it can show up at any scale. So supersymmetry will outlive us all, right? It wasn't a very Bayesian answer, but I think it's a true answer in a sense. We still don't know anything that rules it out in any way. And the reason I think these days to be somewhat confident that it might show up is that string theory does seem to be at least a promising program in quantum gravity, and as far as we know, it can't work without supersymmetry in the sense that we don't know how to really represent fermions in string theory without supersymmetry. And it's still possible that it might solve what's called the hierarchy problem, or the fine-tuning of the strength of the different forces. Right? Why is the gravitational force so much weaker than all the other forces, for example? And possible that it might make grand unification of the 3 non-gravitational forces possible. And another reason, physics-wise, to look at supersymmetry is that, as I hope you'll feel as we go through these slides, SUSY isn't that hard compared to some of the other stuff that we work on in the philosophy of quantum field theory. Okay. As far as philosophy goes, there's some very cool reasons, which have essentially been pointed out prior to my work on the topic by first, well, Robert Weingard wrote this paper on the philosophy of string theory, a few decades ago at this point, which pointed out a number of the interesting issues in the philosophy of supersymmetry. And then some of, essentially a new question about supersymmetry, somewhat different from the ones that, I'll put it this way, somewhat different from the way that Weingard put it, or it might be, you might see it as a personification of one of the ways that Weingard thought about it. Tushar Menon's work has kind of brought out essentially the question of is supersymmetry, is the new geometry posited by supersymmetry we call superspace, is that space-time, right? So philosophy-wise, SUSY involves a new example of explanation by unification because we're unifying explanations for fermionic phenomena and bosonic phenomena, right? So that's an important issue in philosophy of science, obviously. And the most natural formalism to use for SUSY involves positing a strange geometry with more dimensions than we usually think of space-time as having, which is called superspace. So that's where most of the interesting issues come from. So here are three interpretive questions. The first one is the one that Tushar's work has focused on, which is superspace space-time, right? Should we think of it as spatiotemporal, or should we think of it as, another way to put this perhaps, a way to put it that makes it clear that it is a question I think that has content, is superspace the same kind of thing as space-time the way we've thought of it previously? Compare the question when Minkowski came up with Minkowski space-time, right? Is space-time the same kind of thing as we thought of space as being prior to that proposal? The second question, which some people might say is very similar, but I would say is quite distinct, is the question of should we be substantivalists about superspace? And in the way I'm going to use the term substantivalism, as you'll see, you can say no to the question about superspace being space-time and still say yes to the question we should be substantivalists about it. And finally, I may or may not get to this depending on time. There's a question about whether we have to posit the existence of superspace or the spatiotemporality of superspace in order to unify bosons and fermions. Weingard had a view about that I think is wrong. Okay, so here is the part where I'm hopefully going to be teaching you something. What does supersymmetry look like? What is the kind of simplest way to understand the phenomenon? And to do that, we're going to look at the simple harmonic oscillator. Right? So if you have worked through a text on quantum mechanics, you have used the simple harmonic oscillator in what we call, to presage one of the things I'm going to say, you've looked at the simple harmonic oscillator in what we call its bosonic version, where there are unlimited modes of excitation available to the oscillator, right? As opposed to there being, to presage another thing I'm about to say, a sort of exclusion principle that keeps the oscillator from being excited beyond the first mode, right? Let me focus on something that will be useful to you as well if you think much more about the philosophy of quantum field theory just in general. There's this interesting analogy between harmonic oscillators and quantum fields. And this is one of the nice things, if you ever read Paul Teller's kind of, in some ways dated, but also classic book, Interpretive Introduction to Quantum Field Theory. This is one of the things that he brings out very nicely, is this analogy between harmonic oscillators and quantum fields. Or, it's also comes up in Teller's early papers on the topic, and some of Nick and Bob Weingard's work responding to that. There's this analogy between harmonic oscillators and quantum fields. If you look at just a simple harmonic oscillator, okay, you're thinking, well, there's this thing, it has this position degree of freedom, right, and it has some amount of energy, which is how many modes have I excited the oscillator by. Okay. Now, what I want you to do is don't think of that position degree of freedom, right? What is that? Well, it's kind of like, if it's a one-dimensional oscillator, it's kind of like a scalar, basically, right? It's just like a number. What's the position of of the bob of the oscillator. What I want you to do instead is think of that position as the value of a scalar field on one-dimensional spacetime, right? So this is a spacetime with one point of space and, a continuum of time. Okay, so just one point in space, and the field can get more or less excited at that point, and that's it. That's all that's going on in this imaginary world. Okay, so there's a scalar field, and that is the number that is quantum mechanically analogous to the position of the oscillator bob in this example. Okay. So think of the simple harmonic oscillator as being like a quantum field with 1 degree of freedom. In that case, right, a simple harmonic oscillator is kind of a free, that is to say, like non-interacting, because there's nothing for this thing to interact with. It's just one field. It's a free, quote-unquote, quantum field theory on one-dimensional space-time. Now, what does it kind of mean in quantum field theory terms if I excite that oscillator and bump it up to an energy level beyond the ground state? Well, that means I've added energy to it, right? And in the particle picture of quantum field theory, that means excited states or particle states, right? So if I excite the oscillator, I'm adding particles. Essentially, right, the only thing that's going on in this system is, well, how excited is it? That tells you how many particles there are. Right? There's one point in space-time, and the only thing that can happen there is it can be occupied by more or less particles. So quanta of excitation, or modes of excitation of the oscillators are particles. Well, if I add a particle, I've added, I've excited the oscillator by one energy level, right? So that means the energy of one mode is the mass of a particle, right? Because that's the amount of energy that I get if I add a particle to the system. And since these things can't move, they can't have any kinetic energy. So the only energy for the system is the energy of the particles' masses. And as I said before, the position operator is in this case the analog. Well, remember, the position is the analog, the position of the bob of the oscillator is the analog of the field, right, the value of the scalar field. So if we're doing quantum mechanics, we're going to represent that using an operator, and that's going to be analog of what we call the field operator in quantum field theory, which we usually use this symbol phi for. Right. So I will now start to use the symbol phi for that position operator, which is in the quantum field theory analogy of field operator. Okay, so the bosonic oscillator is the oscillator you're familiar with from your textbook. You pick up like Messiah or something, like the Messiah, I guess you're supposed to say. And you look at the regular harmonic oscillator. It's the bosonic oscillator. So just build it up in the usual way. You have a raising operator for the oscillator, which we will think of in quantum field theory as the creation operator, because it's bringing in a particle, right? You apply that operator and you create a particle. A lowering operator, which is the annihilation operator in quantum field theory terms. And the thing that makes this the bosonic oscillator is that those creation and annihilation operators obey regular commutation relations, as opposed to anti-commutation relations, which is what's going to happen for the fermion oscillator. Right? Okay. Now, we can come up with an observable constructed by just, putting a dagger in front of A, which is going to give us the number of particles. That is to say, it'll tell us how many excitations there are in the oscillator. And as I said before, we're thinking of the position operator as a scalar field. And all the energy is going to be in the mass of the particles, so the Hamiltonian is going to be the mass of one boson times that boson number operator. All right. The fermion oscillator is a little bit less familiar, but it's still really similar. The difference is, instead of applying commutation relations to the creation and annihilation operators, so we use C instead of A for the boson creation and annihilation operators. Instead of applying commutation relations, we require that they satisfy anti-commutation relations. Okay. And that has a consequence which is sort of physically evocative, which is if I apply the fermion oscillator creation operator to the state that already has a fermion in it, that already is at the first energy level, then I get nothing back, right? So the energy levels available to the fermion oscillator are just the ground state and the first energy level. So you can only have one fermion in this oscillator, right? So it's an exclusion principle going on here. So we already see some kind of fermionic behavior in this thing. And then we can define the fermion number operator just like we did for the boson. The quote-unquote position operator is going to be a little different. It's going to be a spinor-valued position, quote-unquote, instead of a scalar-valued position. That won't be especially important for what we're talking about. But I'll use psi of t for it, just like we use for a fermion field operator, right? So that's going to be the Dirac kind of version of a field operator here. And we come up with a Hamiltonian just like we did for the boson, where we multiply the fermion mass by the fermion number operator. And that number operator, again, is just going to have eigenstates of 0 and 1, because you can only have 0 fermions or 1 fermion. Now, supersymmetry. See, we're not very far in, and we can already tell you what supersymmetry is, right? How do I make up a supersymmetric oscillator? Well, I create a composite system, right? Just using the usual tensor product way to come up with a composite system. And I put in a boson oscillator, tensor product that thing with a fermionic oscillator, so I got a composite system. And we call it supersymmetric. Well, what's the only difference between the boson and the fermion as far as their energy goes? The only difference is, well, the Hamiltonian, is the sum of the two Hamiltonians, right? And the only difference in the two oscillators in terms of the things that we can notice with our energy observable is the mass of the boson versus the mass of the fermion. So if we stipulate the masses are equal, then replacing one fermion with one boson or vice versa can never change the energy. And I can define these operators, Q and Q dagger. So Q, right, is going to remove a fermion and add a boson. And it's, we have the square root of m thing out front to normalize it. You don't need that technically, but it's makes things more fun and easier to do. And Q dagger is going to remove a boson and add a fermion. Right? These things both commute with the Hamiltonian, which is the sure sign that they are symmetries of the theory, right? So Q and Q dagger, that they generate symmetries, right? So Q and Q dagger are the generators of the symmetry for this theory. Supersymmetry.
Yeah. So if we did this with two harmonic oscillators, just two bosonic harmonic oscillators, we took the Hilbert space for one of them, the tensor product with the Hilbert space for the other, we would think of these as having, like in terms of ontology, having two oscillators, and we could possibly couple these two oscillators. Now, this looks a lot like the same construction, so we have a bosonic oscillator and a fermionic oscillator. So what in this, maybe you'll return to this, so how do we get to this ontological picture where this is actually one supersymmetric oscillator rather than one bosonic and one fermionic oscillator?
Yeah, it's an interesting kind of right, so there's an interesting question here. And there's a lot of levels to it about what sort of, what kind of ontological input goes into constructing the model. Yeah, I think, so in that case, I would say, whether you want to call it one supersymmetric oscillator or a system of two oscillators, a system of two coupled oscillators that in a sense exhibits supersymmetry, that's where I think you might be getting into, this is a purely semantic question territory. What would be in common with that system would be that there would be a symmetry of that system that interchanges a particle from the one oscillator to the other oscillator, right? The system where it was just two bosonic oscillators that were coupled with equal masses. And so, they're not really coupled in any interaction sense, right? But they're a composite system. So in that case, I would say the physically important thing to keep in mind with that system of two boson oscillators is, from the point of view of quantum mechanics or quantum field theory, which might not be all the physical facts there are if you're something like a Bohmian or something, but from the point of view of purely canonical formalism, there's no real physical difference between having one excitation in this oscillator and none in this one, and having one excitation in this oscillator and none in this one. And so then, if you want to think of this model as one where there's two oscillators, a boson and a fermion one in some sense, and there's no fact of the matter about whether you have one excitation in the Fermi oscillator and zero in the Bose, or one excitation in the Bose oscillator, zero in the Fermi, that's another useful way to think about this, and it might be helpful. And indeed, right, there are going to be some invariant facts about, for example, like, for example, if I have a system that I write up as applying, I write up a state applying the boson creation operator like 5 times to the ground state. It is a supersymmetry invariant fact that there are more bosons in that system than fermions, for example, right? So, yeah, that's a really helpful clarificatory question, and I think there's nothing wrong with thinking of this as a system of two coupled oscillators rather than just, two, again, I shouldn't say coupled, but a system of two oscillators that are composite as opposed to like one oscillator. Good. Okay. So, this all looks really normal, right? We've just got a regular symmetry, boring. But, right, the Q operators are stranger than they seem. The reason they're stranger than they seem, in a sense, is because they turn scalars into spinors and vice versa, right? So that means that they have to be spinors in that sense, right? If you have an entity that you multiply something by, and it turns it from a scalar into a spinor, then that thing that you are using for the multiplication has to be spinor valued itself, right? So the Q's have to multiply like spinors themselves. And that's what makes them strange. So they generate what's called a supergroup rather than a Lie group, right? If they multiplied like, in some sense, if they didn't multiply like spinors, if they multiplied like scalars, they would be a regular Lie group, right? But because they multiply like spinors, they generate a supergroup. And that is to say, they generate a supergroup of objects that are characterized by their anticommutators rather than by their commutators. Okay. Another way to put this is that the Q's multiply like. So this is the part of the SUSY stuff that is not going to seem super familiar from your intro quantum mechanics textbooks. Not coincidentally, it's also the part that I feel the least comfortable with myself. As I always tell people, like, I'm not that great at math, but the Q's multiply like Grassmann-valued anti-commuting numbers. Okay, that means that so in particular, right? If I take Q squared or Q dagger squared, okay, the rule is going to say that the anti-commutation rule is going to say that QQ plus QQ equals 0, right? In general, it's going to be Grassmann numbers are going to obey. It's good that you have this, right? Two Grassmann numbers A and B are going to obey the rule that the anti-commutator equals 0, which is to say AB plus BA equals 0. Okay. So given that Q and Q dagger are like that, no Grassmann number can have a non-zero square, right? So you can't have polynomials of order greater than 1 in the Q's or in any Grassmann valued object. And that's kind of funny because, let's suppose I was trying to exponentiate Q, right? Because if I'm thinking of Q as the generator of a symmetry, I'm thinking, well, something like the exponential of q. Okay. Well, that's just going to be like 1 plus q, some factor times q, and then you would have some other factor times q squared plus, q cubed, but these are all gone because you can't have higher order polynomials in these things. So really, there's a sense in which the q's are both the generators and the operators that implement the symmetry. Okay. And here's where here's where we start to see the suggestion of this superspace structure. Right? We'll see a connection now with spacetime. Unlike a regular Lie group, a supergroup, as I was saying, is characterized by anti-commutation relations rather than commutation relations of the generators. Okay. So, I think I said no. So Q and Q dagger, right, are going to have these non-trivial anti-commutation relations. And, if you kind of go through it, right, it turns out that the anti-commutator of Q and Q dagger is going to be the mass times the boson number operator plus the fermion number operator, which is just the Hamiltonian. Okay. So the Hamiltonian, which is the generator of time translations, is one of the generators of the supergroup. Right? If it fits into the anti-commutation relations with some of the generators, it must itself be another one of the generators. Okay. So I can't build a group for this symmetry without including the time translations in that group. Right? In a sense, the supersymmetry transformations have to be thought of as a part of a group of symmetry transformations that includes the time translations. Remember, we're just talking about one-dimensional spacetime here, so the time translations are really like all you have as far as spacetime symmetries go. But this generalizes if I do a supersymmetric field theory on Minkowski space, I'm going to end up with a group called the super-Poincare group, which includes the whole group of spacetime symmetries in this subgroup. Okay. Now that's suggestive, right? Maybe the thought goes, I should try to come up with a formalism where I have some generalization of spacetime, which is the entity that is invariant under this supersymmetry, this kind of supergroup which includes the supersymmetry transformations and also the spacetime symmetry transformations. And I can do this by adding Grassmann valued coordinates to spacetime. So in this case, I'm going to add 2 coordinates, and you can think of them as conjugate. That's why I have theta and theta bar written on there, right? Essentially what I'm doing here, this is a trick that gets used all the time in textbooks on this topic and almost never explained. It's not a very good eraser. But what I'm really doing is I'm saying there's 2 Grassmann valued variables, theta 1 and theta 2, and then I'm saying, I'm renaming them so that theta is theta 1 plus I theta 2, and theta bar is theta 1 minus I theta 2, right? So then I have, it just makes it easier to work with them if they are conjugate to each other. So I've relabeled them that way. That's what I'm doing. So there, I've just saved you some time when you pick up your first actual textbook that talks about supersymmetry and does not explain what I just told you. So now, at this point, right, remember I have these 2 oscillators that are ordinarily represented separately by these fields little phi and psi, right? Well, now I can come up with an object called a superfield, big phi, which is not a field over space-time, which is just the t-axis in this toy model. It's a field over space-time plus these Grassmann value coordinates. Right? We're going to call that thing superspace. Is space-time t plus those theta and theta bar coordinates. And I can represent the fields of the two oscillators jointly using this superfield big phi. I'll just call it phi from now on. And, you know, it's just the boson field plus the fermion field multiplied by the two theta coordinates. And then I add what's called this extra auxiliary field at the end. That's added to make calculations easier. When you construct the observables from the superfield, this drops out and it doesn't matter what you use for it. So it's kind of, people call it the dummy field sometimes. I'm actually a little curious whether there might be some kind of interesting physical interpretation to this thing. But one thing to keep in mind, though, is that from the point of view of what's invariant under supersymmetry, what's invariant is this, and not how it decomposes into this stuff, right? So when you are thinking about things from this superspace perspective, you don't want to think of these components of the superfield as being separate things. That's the kind of the anti-superspace way of thinking about this thing, right? From the superspace perspective, it's really this, and then we can coordinatize, in a sense, the superspace and with a choice of coordinates, break it down into these components. But the whole superfield is supposed to be what's fundamental on this superspace formalism. And then what Q and Q dagger do is actually implement translations on this space of T, theta, and theta bar. Right? They translate you along theta and theta bar. So for example, you might be at theta equals 0 and theta bar equals 0, in which case the superfield is just constituted by the boson field. Right? You might say, like, I only have excitation in the boson part of the oscillator, so this is a pure boson state. Well then, how do I implement a supersymmetry transformation? How do I introduce fermions into this system? Well, I have to create a non-zero Fermi field, right? And that involves, I got to translate myself away from theta equals 0. Okay, so that's the sort of intuitive way to understand that these supersymmetry generators, these Qs, implement translations in superspace. And by coincidence, you know, because of the fact that they don't, because of the fact that they have non-trivial anti-commutation relations with the Hamiltonian, they also move you in time. So if you do two supersymmetry translations in a row, that's going to constitute time translation in this case. And in general, in the super Poincare group, two supersymmetry transformations are going to be a space-time translation. So sometimes physicists use the slogan, a supersymmetry transformation is the square root of a space-time translation. Okay. Now, if we understand superspace as space-time, SUSY is a space-time symmetry. Right? That's the way to think about the stuff I just told you. Now, there's a question, right? Should we think of it that way? That's the kind of one of the kind of philosophical questions in the neighborhood here. But it is available to us at least as a notational tool to think of it that way, to think of SUSY as a space-time symmetry. The question is that the right way from a kind of ontological or understanding the theory in the best way kind of perspective? Is superspace really space-time? So Tushar Menon has written on this topic. You can find his paper on the PhilSci archive, and it is forthcoming in Nick and Chris Lutrick's new anthology. He gives an answer, which is a sort of qualified yes, right? Tushar breaks up space-time into two parts, one of which is the role of theoretical space-time, which is essentially the space-time structure that gives us essentially the structure of geometric symmetries of a system. right? And that's what he calls theoretical spacetime. And of course, a lot of the stuff we've already seen provides reasons to think, yeah, superspace is theoretical spacetime in that sense. He also points out it's not really operational spacetime in the sense. So operational spacetime, he means the spacetime that we measure with ordinary rods and clocks and like light rays and stuff like that. Now, there's a sense in which we do, of course, measure the space we live in with those things, but there's no physically intuitive sense in which you can build a rod that's going to give you, the distances, quote unquote, along those theta dimensions, right? So in that sense, it's not operationally illuminating to think of superspace as spacetime. So from that point of view, superspace is in spacetime. But from the theoretical point of view, in terms of determining the fundamental, well, I don't want to say fundamental because that gets to the metaphysical issue we're talking about. But in terms of thinking about the geometric symmetries of the universe we live in, that should be thought of as the most general geometric symmetries. I'll put Tushar's view that way. Superspace is spacetime. And in addition to this kind of perspective of zone, he kind of connects this with the spacetime functionalism of Eleanor Knox, right? So Knox points out, which Tushar would agree with, but they have somewhat different functional definitions. Knox says spacetime is a functional concept, right? In Knox's case, this is one of the things that will be discussed. I gather that James is going to be leading a discussion group on spacetime functionalism, which is a cool topic. To state Knox's view in one sentence, it's the view that spacetime is the structure necessary to define inertial frames. Knox means local inertial frames, but we're not talking general relativity right now, so we don't need to focus on that qualification. So Knox's view is that whatever, you might say, the kind of minimal structure required, the minimal structure you need to posit in order to tell me what the inertial frames are for a given theory. That's the space-time of that theory. All right. Additionally, there's this famous posit, well, really, kind of two posits that Ehrman gives in World Enough in Space-Time, SP1 and SP2, that what Ehrman calls the dynamical symmetries, which we should really think of as the external dynamical symmetries, because he's not talking about like gauge symmetries, for example. The dynamical symmetries have to match the space-time symmetries, right? So you look at mechanics, you look at Newton's mechanics, and you think, well, we want to posit a space-time for Newton's mechanics that has the same symmetries as Newton's equation of motion, in some sense, right? And Tushar suggests, well, superspace satisfies these criteria. These should be thought of as the criteria for, or some of the different possible sensible criteria. Tushar's own criteria are probably closer to Ehrman's than to Knox's. But these should be thought of as the different possible sensible criteria for what it takes to be theoretical spacetime, right? And the reason why, there's a kind of interesting reason why supersymmetry satisfies Knox's criterion, which I'm not going to go into all the details here, but basically you can define a notion of inertial frames on superspace. They're not force-free frames, right? So because what's the definition of force along one of those theta dimensions? That doesn't make any sense. But what's the definition of motion along those dimensions? It doesn't really make a lot of sense. And anyway, we're talking about field theories, so like force and motion are highly derivative concepts, probably anyway, although Chip Stevens would disagree with what I just said. Maybe not with the motion part, but definitely with the force part. But what we do have is a notion of which frames give the simplest formulation of the theory's equations of motion, right? And that's really ultimately Knox's idea of what is an inertial frame. Or views an inertial frame is a coordinate system that allows us to state the equations of motion as simply as possible. And we do have that notion in superspace, which is the notion of what's sometimes called a superinertial frame. Yeah.
Sorry, I'm struggling a little bit with this. So
Yeah.
can I give an example?
Sure.
So let's say I take instead the electromagnetic field, and I have some scalar that defines its value at every point in space-time, and I just tack that onto the vector that tells you, that defines your inertial frame at every point in space-time. So now I'm constructing some super space. It's not this super space that you're talking about, but it gives you more information in a, some would argue, simpler form than you can get by defining the theories separately. And I would say that you could, under your definition, you could say, well, this is the structure necessary to define inertial frames if you say inertial frames are the way you define them, and I would say that's sort of contrived.
Yeah, it is. I mean, there's something here which I very much agree with, which is that there's a bit of arbitrariness in Knox's privileging of the stuff that she does privilege. You know, it's like, so, I mean, spoiler alert, I don't agree with Knox. I have quite a different view of how to be a space-time functionalist. She would say, right, that it's not that the inertial frames are the frames in which the theory as a whole can be expressed most simply. They're the frames in which the equations of motion in particular can be expressed especially simply, right? So that's, I think, where she would say you can't find, you know, you can't define. I mean, but there's another thing in your question though, which I think I do really fundamentally agree with completely, which is we could come up with a new definition of inertial frames by changing which kind of coordinate systems we're writing the theory up in, right? So like ordinarily we write electromagnetism in four-dimensional coordinate systems, you know, for using regular spacetimes. Could you come up with a different version of it with higher dimensional, like quote-unquote geometries, and define your inertial frames differently with those, right? I actually think that what this kind of example shows is that Knox's picture doesn't have the resources to like tell the difference between those things, because essentially her criterion for inertial frame is give me a bunch of different coordinate systems that are all kind of like the same type of coordinate system, right? So they're all tetrad fields of the same dimension, which is to say like they're all coordinate systems, you know, like four-dimensional coordinate systems or something like that, right? So she says, give me a theory and give me some coordinate systems on it. Maybe they're four-dimensional ones. And then I can tell you which of those are the inertial frames, because they're the ones where the equations of motion take on the simplest form. What if you gave her eight-dimensional coordinate systems, right? Well, there might or might not be an answer to how you would make the I don't know what the analogy of equations of motion would be, but you might be able to come up with some analogy of them and come up with frames of those sort in which they were as simple as possible. And then you could say to Knox, well, which ones give me the real spacetime? Is it the four-dimensional ones that I can give you and get the, you know, the inertial frames from those, or is it the eight-dimensional ones that I can give you and get the inertial frames from those? And she wouldn't be able to answer that question, right?
But, I mean, sorry, just
yeah.
imagine like one of the, like these questions were sort of discussed in the beginning of general relativity. You know, they're like, because of all this interpretation of, oh, you know, the general relativistic field is some geometry, they're like, well, can't we just interpret the other fields as geometry?
Yeah.
The reason they threw it out, but the reason they said no, or the reason you privilege the space-time metric we know and love, is because of universality. So it seems to me that if you want to use one of these criteria to privilege superspace, the supersymmetric superspace, you also have to privilege all of the other superspaces you can build with other fields. And then you have to choose your reason why you think the supersymmetric superspace is important. And if your reason is because supersymmetry does other things for us, that's fine, but you can't say that it's somehow unique.
Yeah. Yeah, I mean, I as an application of Knox's view, I totally agree with you. Because I think essentially, right, Knox's view doesn't give you the resources to say, should I take a supersymmetric theory and input 4-dimensional coordinate systems, or should I take it and input, 6-dimensional coordinate systems with the 2 Grassmann coordinates included, right? Her picture just tells you what's an inertial frame, given that you have handed her a set of coordinate systems, right? This is this is very closely related to one of the criticisms of Knox that I mentioned in the kind of written version of the paper. It's I think there's a serious problem for review here, and you're exactly right in a way about what it is. Yeah. Okay. Which is really good, because I was kind of hoping that I'd be able to get to that in some form in this talk, but like I wasn't sure I was going to. Okay. So here's my reply to what Tushar has to say, right? And this is closely related to my reply to Knox's view as a whole. So my concern about Knox's view, and it's also my concern about Tushar's view, is that it doesn't seem to me like theoretical space-time is the sort of concept that can have a single, simple bunch of necessary and sufficient conditions, right? It's not like, being a bachelor where you're like an unmarried, man or whatever. It is more like folk concepts of animal species or something like that, right? Where you think, what is it to be, think of a species that doesn't really exist because that makes it easier. You don't have to talk about its genetic code or evolutionary inheritance. Think about unicorns, right? Well, to be a unicorn, it helps to have 4 legs, but surely, it's such a sad, this is such a sad thing to think about, a unicorn with a missing leg. It's really funny, I just revisited The Last Unicorn. Everybody ever watched that movie? It's a classic animated, beautiful movie. So the thought of a unicorn missing a leg makes me even sad. I think of a unicorn voiced by Mia Farrow missing a leg. But if I imagine a unicorn is missing a leg, it can still be unicorn, right? It's just that having 4 legs helps you count as a unicorn, right? It gives you unicorn points. Having a horn, if you had your horn cut off, you might still be a unicorn. God, this is. If you had your horn cut off, you might still be a unicorn. But right, it helps, of course, a lot to count as a unicorn if you have a horn, an intact horn. So unicorn seems like a cluster concept, right? It's one of these things. Of course, Wittgenstein famously talks about the example of a game. Berescout talks about the example of art as a cluster concept. The idea being there's no single necessary and sufficient conditions for it. Instead, there's a bunch of different factors, and if you meet enough of the factors to enough of a degree, you count as art or as a game or as space-time, right? That's how I like to think of space-time. There's no necessary and sufficient conditions for being space-time. There's just a bunch of different criteria, and if you meet enough of the criteria to a high enough degree in a given theory, then, in other words, let's talk precisely here. If I have a type of structure in a given theory, and I think, how well does it meet different criteria within that theory? Like, one of the criteria, I agree with Knox, is explaining the inertial structure of the theory, right? That's a big job. But there's other ones, Operational criteria, like the ones that Tushar mentions, are important ones. Do rods and clocks measure this quantity, right? And the case of superspace actually shows that it's possible to meet those inertial criteria without meeting those operational criteria, right? There's other things you can think of, like giving us the distances along which forces fall off and stuff like that, right? So the extra superspace dimensions, well, they satisfy Tushar's conditions for theoretical spacetime. They may fail others, and indeed, as he notes, they fail the criteria for operational spacetime. In a way, this is a place where we're sort of separating our questions, because I would tend to say, I'm not sure I have exactly a separate concept of theoretical spacetime. Instead, I might say I have kind of a unified concept of spacetime, and the theoretical and operational parts of it both count towards that cluster concept. But additionally, right, the extra superspace dimensions might fail other conditions besides the ones that are two-shot notions. Now, I want to talk about some further criteria that I think are plausible, in particular the fundamentality criteria, right? So it seems to me that pretty much everybody, substantivalists and relationists disagree on a lot. One thing they agree about spacetime is that in some sense, the facts about spacetime are highly fundamental facts, right? For the relationists, they're highly fundamental, not facts about ontology, but facts about what relations hold between the things that exist. Whereas for the substantivalists, they're fundamental facts about what exists. This substance, spacetime, exists. So everybody agrees that spacetime is highly fundamental. And it's probably not perfectly fundamental, unless Tim Maudlin's pessimism about essentially all programs in quantum gravity research that are going on now, unless that pessimism is justified, or unless one of these sort of, I should put that in a different way, which is unless one of these Bohmian research programs is trying to recover fundamental spacetime from quantum gravity succeeds, it looks like we might give up on spacetime as a fundamental notion. Just that's the direction that most research programs in quantum gravity are going. But still, it's going to be a highly fundamental. Spacetime is going to be a highly fundamental structure. It's about as fundamental as anything that we have a good theory of right now, which makes it highly fundamental. So I'm thinking, if I look within my own, this gets to the point where question about concepts can be kind of semantic questions in a way. But if I look within my own heart at the question of what counts as spacetime, I think, well, if it's highly fundamental, that makes it more apt to count as spacetime. Another type of example that's helpful to think about this is you think about a structure that's isomorphic to spacetime in some kind of computer simulation or something, right? Is the spacetime that they seem to live inside in the matrix a spacetime? Is that really spacetime, right? Well, I would say no. Why not? I mean, it has all of these functional geometric characteristics that we associate with ordinary spacetime, but it's not very physically fundamental. It's made up out of electronic goings on. So that's why I don't think the spacetime of the matrix is a spacetime. If I'm correct about that, maybe I'm not. That's an interesting debate to have. But it seems to me that fundamentality ought to be one of the criteria for the spacetime concept. If it is a criterion, then that means we have to answer the substantivalism question prior to answering Tushar's question about whether superspace is spacetime. Because I take the question of substantivalism to be the question of whether, the question of spacetime substantivalism is the question of whether spacetime is a fundamental substance. Right? So the question of substantivalism about superspace is the question of whether superspace is a fundamental substance. And it might be a fundamental substance and not count as spacetime, right? Like an electron is a fundamental substance and it's not spacetime. Electron's probably not fundamental, whatever. Relatively fundamental. So I think this might be a borderline case, right? And as I mentioned before, Minkowski spacetime defines the interactive distances for forces, and it has all those operational characteristics. So this might be a case where, it's not exactly settled whether our existing concepts are going to count superspace as spacetime or not. But I want to just talk briefly about the substantivalism question because I think that's actually the most meaty question philosophically. It's a real metaphysics question, right? Which some people don't like that, but I do like it. So here's my definition, which is Jill North's definition, really, of what it is to be a substantivalist about space-time, right? You're a substantivalist if you think space-time is at least as fundamental as matter. That is to say, if I tell you all the fundamental facts about matter, I've still left out the fundamental facts about space-time. That's substantivalism. Now, for a non-fundamental theory, like general relativity is not a fundamental theory, but I am a substantivalist about general relativity. What gives, right? How can I adopt this attitude towards a theory that I think is not a fundamental theory? Well, in the case of general relativity, what I want to say is that space-time is among the most fundamental structures in the domain of application of general relativity, right? It's one of the most fundamental structures we try to describe using general relativity. We don't try to describe, spin networks using general relativity or something. So even though spin networks might be more fundamental than space-time, I'm still a substantivalist about general relativity because I believe that space-time is one of the most fundamental structures in general relativity. So this is the sense in which you can be a substantivalist about a non-fundamental theory. So now, right, supersymmetric quantum field theory is also not a fundamental theory. But I can ask the question similarly, whether you should be a substantivalist about superspace in supersymmetric quantum field theory. And in that case, I take that question to mean the question of which is more fundamental, superspace or Minkowski spacetime. So here's one argument in favor of being a substantivalist about Minkowski spacetime and not superspace. The idea that superspace might be a sort of surplus structure, right? It's extra. We don't need it in order to do the work. We can write up our supersymmetric quantum field theories in Minkowski space. Why should we add this extra structure? It might be calculationally useful, but why should we posit it as part of our ontology? And there's a sense in which it is surplus structure, right? Because there's kind of, if you look at the paper about this that I sent out, I talk a bit about this, and there's some stuff that I cite which is incredibly, it's algebraic quantum field theory, from a mathematical physics journal, so it's incredibly difficult to read kind of stuff, but I have corresponded with one of the authors of it, so I understand it conceptually, which is all that I need for my purposes. So what these guys show, or it's actually a conjecture, but they show it in the case of this oscillator model, and they're pretty certain that it holds in general, is that, and it has to be true in general, right? It would be crazy if it wasn't true. Superspace and Minkowski space versions of a given supersymmetric quantum field theory have the same algebra of observables, right? That is to say that they're characterized by the same physical kind of measurable quantities within the ordinary quantum formalism, right? And again, if you want to have a hidden variable theory, you'll object here and say, well, the observables aren't all the real physical quantities. But within canonical quantum formalism, superspace and Minkowski space versions of the supersymmetric quantum field theory have the same measurable quantities. So, right, why would we need the extra superspace structure when we can define all of the measurable quantities we need on the Minkowski spacetime, right? We have a rigorous equivalence between the two algebras of observables. So in other words, if I take a given supersymmetric theory and I write it up on Minkowski space, and then I take the same theory and I write it up on superspace, what these mathematicians think is that, yeah, there's a rigorous equivalence between the algebra of observables on this Minkowski space theory, which we call the component theory, and the algebra of observables on the superspace theory, which we call the superfield theory. Okay? And we don't usually think of operators other than observables as having physical significance. Field operators themselves, well, they're not invariant under the symmetries, right? So we usually think of them as physically uninteresting or physically unreal. In other words, the invariant, a way to put this is that the invariant structure, the invariant observable structure of the component theory and the superfield theory are the same. The difference is one of them is on Minkowski space and the other one is on superspace. Right? So why do we have to add this extra superspace structure, these extra, Grassmann value dimensions? Perhaps the superspace structure is explanatorily needless. Well, it is and it isn't. Right? If I just look at a theory by itself and say what role is the superspace structure playing in explaining the phenomena within that theory, this equivalence in a sense kind of shows us that it's not playing any predictive role, any role that explains in that way. But it might explain something else which is important, right? It might explain the fact that supersymmetry is a symmetry. Okay, so here is an argument for superspace substantivalism. This argument was suggested to me by James Wells, who's one of our theoretical high-energy physicists at Michigan. And I went to James and I asked him, James, which do you think is more fundamental? Superspace or Minkowski space in supersymmetric field theories? And he's like, oh, superspace. I said, why, James? And he said, because if superspace is fundamental, then you have an explanation for why SUSY is a symmetry. Because, the way he put it is, there's no way to write up a theory that isn't invariant under supersymmetry in superspace. Whereas there is an easy way to write up a theory that's not invariant under supersymmetry in Minkowski space. So we have a sort of explanation for why SUSY is a symmetry. In order to turn this into an argument, I have to add a premise, which is that fundamental geometric structure can explain symmetries. Right? And I grew up thinking that this was an uncontroversial premise, and in a move that has been really useful, even though I think it's ultimately misguided, in a move that has been really useful to the philosophy community in understanding the logical relationships between things, Harvey Brown has challenged this premise by suggesting that, no, dynamical symmetries are not really governed by fundamental geometry. There's no sense in which space-time forces the theories from the space-time to have the same symmetries as the space-time. Instead, Brown thinks like, well, the explanation goes the other way. You look at what are the laws, what are the dynamics in a world. You think, what symmetries do they all have in common? Oh, those got to be like, this is simplifying, but those are the symmetries of space-time. Right? So I am taking on board what I take to be a more sort of classic in defense of dogma kind of view against Brown, that fundamental geometric structure can explain symmetries. That if I tell you the space-time we live in is Minkowski space, for example, that can provide a good explanation for why the right theory is Lorentz invariant. Right? And we can talk, we'll talk I'm sure we'll talk in the space-time functionalism discussion about whether this is a great assumption to make, but I think it is a good assumption to make. Then, right, if superspace is fundamental, we can explain why supersymmetry is a symmetry, because superspace is fundamental. It's the fundamental geometry of our world. I'm not going to call it space-time now because it's a separate question whether it's space-time, but suppose it's the fundamental geometry of our world. The symmetries of nature have to match the symmetries of the fundamental geometry of our world. So, if superspace is the fundamental geometry, then we have an explanation for why, in our oscillator example, the mass of the boson and the mass of the fermion are the same. On the other hand, if we didn't live in superspace, if we lived in ordinary space-time, we could ask this kind of fine-tuning question, in a sense, why is the mass of the boson the same as the mass of the fermion? And there would be no answer. Right? It'd be a brute fact. You want to reduce the number of brute facts, you want to explain them. Superspace provides a way to do that. So this, I think, there's a bunch more arguments you could potentially raise for and against superspace as a fundamental substance, but this, I think, is a pretty good one So I think this is a good place to leave it and kind of open things up for discussion. I don't know how you guys want to run this, but
Can we take questions? 'Cause I
yeah,
need to
totally.
talk to Tom on
What's
the
that?
side.
What's up?
Yeah. Thanks for the talk. I was wondering the thing about the algebra of observables being
Yeah.
the same.
Yeah.
I was a bit puzzled because of course you have all this structure in superspace that
Yeah.
you don't have in the Minkowski space thing. And I was wondering if you could construct some artificial kind of looking artificial observable with these things. And then you would say, well, but you cannot measure them. And you
Yeah.
would say, of course you cannot, because if you can only measure things with rods and clocks,
Yeah.
then you are restricted in some way. But maybe you can build out this kind of observables in these extra structures.
Yeah, I mean, you can absolutely construct operators that are not. I mean, so like you know, any combination of these components of the superfield, like basically other than the superfield, is going to be definitely an operator, right? That is not going to be constructible in the Minkowski version of the theorem, right? You can construct it in the superspace version. You can't construct it in the Minkowski version. So yeah, there's going to be a bunch of operators like that. Let me make an analogy, right? So so take just a regular fermion field. This I wish I had an analogy that would be more helpful to people who weren't kind of already quantum field theory people, but I'm not sure I do. But maybe this will be helpful. Yeah. So just take a regular Fermi field, right? All of the observables. So here's the difference between boson and fermion field theories. In boson field theories, all polynomials of the field operators are observables, right? Which is to say, all of the polynomials in the boson field operators are invariant under the symmetries, and so you're right that measurability is kind of a weak condition, and it's like, yeah, we want to have all kinds of like physical quantities that aren't measurable, but being invariant under the symmetries, I think, is an even more kind of basic requirement. Okay, so sorry, to get back to what I was saying though. In boson field theories, all polynomials of the field operators are invariant under the symmetries, and so are observables. In a fermion field theory, only even polynomials of the fermions, of the fermion field operators, are observables. And there's a kind of deep reason for this, which is that the fermion field operators anti-commute at space-like separated distances rather than commuting. And so if you were to say they could all take on values together, you would get a jumble, right? Because, or another way to put this is, they don't have like real eigenvalues in the way that the Bose field operators do. So you have to restrict which combinations of the fermion field operators you're allowed to use to construct observables. And then we tend to say the odd polynomials of the fermion field operators, they're not real physical quantities, they're kind of calculational tools, right? They're useful in putting the theory together, but they're not part of the real physical content of the theory. That's at least the sort of prejudice that I was bringing to my discussion of the superfield, that only the operators you can construct out of the superfield that are going to be invariant and so count as observables in that sense, only those operators are going to have physical significance. Yeah, that's essentially where that assumption is coming from. But if you were to ditch that assumption, then it's totally true that there'd be a bunch of other functions of the different operators that you can put together that would not be available.
So there are not invariant. There are no invariant operators that only live like in the Grisman or like just with Grisman invariant.
Yeah, that's right. Yeah, there's no invariant operators that are there's no invariant operators that are going to be non-trivial functions of the Grassmann. Yeah. Oh,
It's
yeah.
a very small follow-up on this, and if it's technical, don't worry about going into it. But
if it's technical, I
is
probably don't know.
is
Especially
the
given
equivalent
ask.
supposed to be robust up to other things that you might not consider to be part of the native theory, but you might want to do with the algebra of observables? So, and here's an example of concrete example kind of I'm thinking of. We know that we can localize a rigid symmetry and get a gauge theory, right?
Yeah.
Turn interactions. It's also generally thought that the strategy for constructing gravity is you localize. In this case, so you localize supersymmetry and you get supergravity,
Yeah.
right? And generally
Yeah.
people do that trick within the superspace formalism.
Yeah.
So is this something that the equivalence is robust up to?
I would bet that it was, but I don't know the answer to that, Nick. Yeah. I mean, it would be weird if that was not true. So I suspect it has to be true, but I don't really know the answer. Okay. Yeah.
It's a question about the general metaphysical picture. So let's take for granted substantivalism about superspace, and that spacetime is not superspace.
Yeah.
Then one question would be, should we be substantivalist about spacetime or not? And it seems that according to North's definition, we should be, because it could be as fundamental as matter. And you said at some point that, well, if spacetime is fundamental enough, we should be substantivalist in some sense.
Good.
But still, from another point of view, it's less fundamental than superspace. And if superspace is absolutely fundamental and space-time is only relatively fundamental, then there is a kind of tension. Maybe it's just a semantic tension. But
No, I think it's not. I guess what I was probably assuming here is that if we take the point of view that superspace, well, no, actually, this is good. Okay. I was about to say something that was in extreme tension with the answer I just gave to Sebastian. Okay. I was about to say that if we think that superspace is fundamental, then we would want to say that matter is given by the superfield, but that doesn't fit with the answer I just gave to Sebastian. The answer, I would want to say if superspace is fundamental, then matter is given by the algebra observables of the superfield, which is the same as the algebra observables of the component fields. So you're right. We have the same algebra observables. This is a very rigorous sense in which you're right. We have the same algebra observables we're treating as the matter. And the question is, do we treat the space-time as the superspace that we can define that on, or do we treat it as the Minkowski space that we can also define the same algebra observables on? So, yeah, right. I mean, one point of view you could take is that the most fundamental constituents of a quantum field theory are its space-time, its geometric setting, together with its the observables characterizing the matter of the theory, right? And then from that point of view, if those two inputs were superspace plus the superfield algebra observables, then it would kind of just follow from that Minkowski space is not part of the really fundamental structure, and so it would be less fundamental than the matter, right? Yeah, I'm not 100% sure that that's the way we look at it, but that's one way to look at it that would address this concern.
it's a definition of forces.
I think there is a really substantive question there. It's delicate work to avoid making it a semantic question. So I may not have succeeded with that. Alex.
Oh yeah. So I agree that the explaining that supersymmetry is a symmetry is like a pro tanto reason for being a substantivalist about superspace. And I was thinking there might be like two, possible responses. I wish I had like a more concrete example. But like one would be maybe that argument would overgeneralize. Maybe there are other cases where these symmetry, like some symmetries, and then you can define some sort of space, and then the argument, this is maybe not super charitable because you're not saying like in every case that's a sufficient reason for being substantivalist.
Yeah, my view is it is just a pro tanto reason for sure.
Right.
Yeah.
But yeah, so I wish I had a better example for that. But then another worry would also be that maybe being a substantivalist about superspace would then raise other explanatory questions that might be then harder to answer, like explaining why ordinary space-time is what's singled out in our perception or something like that. Now maybe you could still answer that with the tools of like a functionalist approach to defining what space-time is, but the more space-time like substances there are, I feel like the more those kinds of questions become less.
Yeah. I mean, I think in the second case you would want to give a functionalist answer to, and so basically one would be in the same boat with David Albert in his picture of why regular space shows up out of configuration space, which I think is basically being a pretty good company. I mean, not that I'm a configuration space realist, but I think that aspect of Albert's view works fine. On the first part of your question, right, I think a good analogy would be, why aren't we, for example, like let's write up a gauge field theory, just electromagnetism or something. Why aren't we substantivalists about the whole fiber bundle that we could write that theory up on, right, as opposed to just space-time? And maybe we should be. Some people have said that they were fiber bundle substantivalists. I think there's a particular reason to be a superspace substantivalist in this case, because, unless you're a relationist, which you don't want to be a relationist, that's a joke. I take relations very seriously. But although I am a substantivalist, so unless you want to be a relationist, you're either going to be a substantivalist about Minkowski spacetime or a substantivalist about superspace, right? And superspace is not that much of an extra commitment over being a substantivalist about Minkowski spacetime. And so, you might think like the extra explanatory gain is worth it for the very small additional ontological price, as compared with like being a realist about like the whole fiber bundle or something, which is kind of a weirder structure. But superspace is a weird structure. That's kind of how we apply it.
Okay. So just asking it, in what sense exactly do you mean that substantivalism question is somehow prior to Bennett's question?
So good. So that's helpful because I feel like I wasn't very clear about that. So let's suppose that I say yes to the question about superspace substantivalism, right? Well, if I'm asking the question about whether superspace is spacetime, part of that is, so I'm looking at Minkowski space, I'm looking at superspace, I'm thinking which of these two things is spacetime, right? And one thing you might do, there's a version of functionalism where you say it's not exclusive, right? It's like it's not as if there can be only one. Maybe they're both spacetime in a sense, right? Depends on how exclusive you want to be. But suppose you are an exclusivist and you think there's only one spacetime for a given theory. Well, Minkowski space and superspace, they both look pretty good from the point of view of whether they're spacetime, right? It might be that one of them being more fundamental than the other could break the tie here. So if I say, it might be that they're tied on their other virtues and vices with respect to whether they count as spacetime, so that I think, oh, well, if Minkowski space is the more fundamental one, then that's going to push it over across the finish line, and that'll be spacetime. But if superspace is more fundamental than Minkowski space, that would push superspace across the finish line, and that would count as spacetime, right? So it's not necessarily going to break the tie, because it might be one highly credible view is, well, look, the operational criteria are going to push Minkowski space to be the winner anyway, right? Because those operational criteria are very central to our spatiotemporal, our overall spatiotemporal concept, right? But if you don't think that, if you think that they're tied on the other virtues, then fundamentality might push one or the other ahead. That's what I was thinking might be a tiebreaker. Tushar has like a thought.
Yeah, just a finger on this.
Yeah.
I have a bunch of questions, but I think I'll save those for the discussion.
Yeah.
Just a finger on Niels' question. Why is fundamentality then prior to the spatiotemporal to Menon's question, rather than orthogonal to it?
Yeah. Well,
couldn't my view on whether or not it's spatiotemporal inform my view on whether or not it's fundamental?
So this is interesting. I mean, so like, okay. So in the evidential sense, yes, but not in the kind of order of explanation sense. So let's think about let me make an analogy with another cluster concept, right? So like, I have, somebody hands me a box and they're like, hey, you got to figure out if this contains a game, right? And the box has like, like sorry in it or something. And so I could proceed one of two ways, right? I could look at inside the box and see, oh, it has rules and there are turns in this activity that you use these pieces for. That would be evidence that it was a game, right? On the other hand, I might go to a bunch of people I know and trust and say, hey, I haven't looked inside this box that says sorry, but I trust you. Tell me, is this a game? And they could say, yeah, it is a game, right? Like I played that when I was a kid, it's a game. So now I've gained evidence that it's a game. And that gives me a bit of evidence that it has turns, okay? So I can either proceed by trying to find out if it's a game and raise my credence that it has turns, or I can proceed by finding out that it has turns and raise my credence that it's a game, right? But for explanatory purposes, I think figuring out that it has turns and discovering thereby that it's a game gets the error of explanation right, whereas figuring out that it's a game and thereby inferring that it has turns gets the error of explanation wrong. That's what I would say to that. Jamie?
So when people say that dynamical symmetries are governed by fundamental geometry, I think that there are various things that one could mean. Some of them seem to me to be fine, some of them seem to me to be less fine. So here's a sense in which I think it's fine. Consider, say, the massless line coordinate equation coupled to a Minkowski metric field, and then ask why is that on the Graham variant? There seems to be a legit explanation to say, well, it's coupled to a Minkowski metric field, which is ontologically autonomous. That explains the symmetries of this equation. Here's a sense in which I think it's not fine. Write down a piece of geometrical structure like a Minkowski metric field, and then the thought is that simply in virtue of having written down that piece of geometrical structure, I can only have dynamical equations which manifest the symmetries of that piece of structure.
Yeah.
And it seems to me that principally it's the second which is criticized by, say, Brown and Cooley. So they say something like, as a matter of logic alone, it doesn't follow that by writing down a piece of geometrical structure we have to have dynamical equations with certain symmetries. The thought is that we could have other pieces of geometrical structure to which the matter fields couple such that their dynamical equations don't manifest their symmetries.
Yeah.
Those symmetries of that initial privileged piece of geometrical structure. So I was wondering which of these two views, the former or the latter, you are more closely aligned with when you made this claim that dynamical symmetries are governed by fundamental geometry.
Well, I think it's something that's a little bit between, because I absolutely agree with Brown that like there's no mathematical or logical or metaphysical necessity that says that any Ij needs to always like govern the symmetries of matter fields in the world that it's defined on. What I would say is that it is, I'll put it this way. The following hypothesis makes sense to me. I can take an 8ij, you know, the substance represented by it, the geometric substance represented by a metric, and declare that it is a fundamental background, which to me amounts to saying it's a law in the world where that metric exists, that all of the fields in that world have to obey the symmetries of that metric. Right? I can say that that's a law. And that's not the same as taking it and coupling it to a particular other field and saying they share the same symmetries. Instead, I'm saying, like, this metric is a substance, and it's the sort of substance that governs the other matter substances that might show up in the same world.
Yes, I think I actually agree with you that if you make the stipulation that this is the only piece of geometrical structures which you're happy with,
Yeah.
then this can explain all of the symmetries of all of the matter.
Yeah, I think Brown might also say there's a sense in which you can make that stipulation, but it doesn't make sense to say that that stipulation is a law of nature.
Yeah.
I think Brown would say it doesn't make sense to say that stipulation is a law of nature, whereas I think it does make sense to say that that stipulation is a law of nature. Got a couple minutes left. Is there any questions?
I have just a program question, which might be slightly provocative, but you can feel free not to answer it. You mentioned this idea of your friend or colleague in Michigan who claims that superspace is more fundamental because it can explain the symmetry. I guess I would like your comment on how you judge the ontological weight of accepting this superspace as a greater space over just positing that the mass scales are similar.
Yeah. So there's two ways to read that question. One of them is, which is a more reasonable posit, and the other one is there anything to the one posit over and above the other? So which of those two questions are you asking?
I don't want answers to both, but
Okay.
the latter would be primary.
Yeah, I mean, right. So I think one way to answer the latter question would be to say, you know, it's a little bit related actually to what I was just saying to James, right? Because there's a difference between saying X is a law of nature versus saying that a law of nature of this particular type governs this particular structure, right? So, like, for example, I might say it's just a law of nature. So like, here's a weird, implausible system of laws, right? Like, I chuck this pen, and we look at the exact trajectory it takes, and I say, it's a law of nature that this pen would take this exact trajectory, right? Like, this exact pen, this exact object would take the exact trajectory, this one, right? Or I could say, it's a law of nature that the trajectory of the pen would follow a geodesic in, you know, the space-time that it exists in, right? I guess that wouldn't really happen, but just whatever. You know, I let it go. So, to me, positing that it's a law that the masses are the same. I mean, you could say it's just a coincidence that the masses are the same. That would be weird. But like, positing it's a law that the masses are the same is, you know, it's a law that's kind of like, that's kind of dictating particular facts in a more direct way, as opposed to saying, you know, there's superspace and it's a law that the symmetries of matter have to mirror the symmetries of superspace. That's kind of a law that dictates circumstances in a more general way. And you know, it's a bit fuzzy. The theoretical virtues are really hard to pin down, but it seems to me that we like laws that dictate the circumstances in a more general way.
Oh, certainly.
Yeah.
I understand that. My question is, you know, we can. This sort of goes back to. Go ahead.
Yeah. Okay. Good. So now the difference. Sorry. Am I wrong, or were you about to say you were asking a question about what's the substantive difference between those two hypotheses? Is that right? Yeah. That's what I thought you were about to say. Because you're right. I like turn your question into something different. Okay. So.
Just a second.
Yeah, sorry. So, okay, so here's a question like, what's the difference between a law that says every object that actually exists follows every exact trajectory that it follows, versus a law that says, like, as a general matter of fact, objects will follow these geodesics, right? In other words, one of them has a kind of like more unifying structure, one of them has a kind of like more particular structure, okay? But the specific answer is, you know, I like the idea that's coming out of contemporary metaphysics that some of the structures in our theories are fundamental, others are derivative, and the question is the space-time structure more fundamental or the laws dictating the mass is more fundamental, right? Okay.